Morning, everybody. Let's get started. Hello. We better get started before the jokes get too risque. Okay. So I'm going to go through it quite quickly because most of the stuff we've done before, we just have to check that the new ChemSep additions make it work. So we'll go straight ahead. Create new with Wizard. I like to close. Oops, I can't close it yet. So let's go to next. We're going to choose monoxide, dioxide, hydrogen, water, and methanol. LMN. Methanol. Okay, I think that should be all. Let's just do the click over there on search. No, I think we've got them all anyway. 1, 2, 3, 4, and 5. Next, and we'll do Peng Robinson first. So yeah, last time we used Peng Robinson and it crashed, but I was surprised because Peng Robinson is the more it's the more secure, stable of the of those property packages. So we'll add it, and we'll also add in NTRL, NRTL, in there it is right here, as a second option. All right, and we'll go to C5, degree C, bar, kilograms per hour, finish. All right, now I'm going to put together the flow sheet from left to right so that we can check that everything goes blue as we create the flow sheet. So we'll start off with a material stream, and we will leave the temperature there. I'm going to change the pressure to exactly 1 bar. No, it's 20 bar. Okay, and it is correctly. Oh, let me close this window, give ourselves more space. So it is correctly executing, and we need to change the compound amounts. So here we're going to have 0.4, I think. Yeah, 0.4 at water is 0.6. 0.4, and just change the rest. Hydrogen is 0, and this one is 0.6. That's water, that's correct. And this one is 0, and accept changes. Total is 1. It's all very happy, and I'm very happy as well. Stream conditions, 20 bar, 25 degrees C. Okay. And 3,600 kilograms per hour. Yes, still got that. Okay, so now we go on to the next thing, and that will be the Gibbs reactor. Choose reactors, Gibbs reactor, chuck it in there somewhere. We click on it. We use the inlet stream as MSDR01. We create the other streams, and we choose outlet temperature. It is the more stable of these 3 options. It's a pity they make the adiabatic the default. That is one of the least stable. And pressure drop 0 is fine. Peng Robinson. But we need to choose the compounds. See, if we choose methanol, it is possible for these things to automatically be converted to methanol. So we just want the water gas shift reaction happening. And if we choose only those 4, that's the only degree of freedom we have, is for the water gas shift reaction to occur. Because the water gas shift reaction, you'll probably execute in a different reactor to the methanol synthesis reactor. In Fischer-Tropsch, the iron catalyst that Sasol uses is very strong on supporting the water gas shift reaction, and for that reason it makes CO2 instead of water with the Fischer-Tropsch reaction at Sasol. Okay. If you use NaCl in the Gibbs reactor, oh, it doesn't solve. All right. Yeah, I tried this thing when I did the stat of deleting. Once it was solving, I deleted these liquid lines that would be empty, that would have zero flow, and then it stopped solving. So I wasn't so sure whether it was the NaCl itself or because I deleted the liquid streams. So I had to add in the liquid streams afterwards, and that's why you'll see that they've got numbering, they've got naming. I've called them LSDR and VSDR on the next one, simply because I deleted them and I had to add them again. And this program doesn't create new streams as well as it should. So sometimes it creates new streams with the same name, and I had that problem when I did this previously. All right, so this is not solving yet. We've got the compounds, parameters, define outlet temperature. We want to define that as 900 degrees C. Oops. Trying to solve, and it solves. Okay, cool. All right, so that means we can carry on. So we add the next one is a conversion reactor. And just need to look, RCO1, that conversion reactor, we'll choose it. We will hit an inlet stream of MSTRO2, the vapor, yes. And we will create outlet streams and energy stream. And I'll fix the energy stream, yes. And now we've got to do our reactions, and that to get to that we have to do the settings. And drag the window up for you. And the settings for the reaction is reactions. Create a new chemical reaction, it's a conversion. Drag that up. We include carbon monoxide and hydrogen to make methanol. And the base component is going to be the one that is limiting stoichiometrically. So we choose hydrogen as the limiting as the base component. Stoichiometric coefficient, we're going to use up 1 carbon monoxide. We're going to use up -2 hydrogen. We're going to make 1 methanol. And now we have a look at the balance, it's okay. And we know that the phase must be in the vapor phase, and base component is hydrogen, conversion is, what did we say, 90, I think. Methanol synthesis reactor, conversion equals
90%.
Thanks. I can close this now. Now we're back at this reactor. And we want to define the outlet temperature, and the outlet temperature we want to be 250 or 200, let's see, 250, yeah. The pressure drop 0 is fine. I actually said 20 bar. Oh no, I didn't. That is the gas liquid separator. Delta P equals naught. Yes, I did say that. And why is it not solving? There is no material stream connected to the outlet of the reactor. Only got one outlet. And look at the beautiful color that it becomes. All right, that is RCO1. The next one is SEP01, gas liquid separation. Separators, tanks, it's a gas liquid. We stick it up here somewhere. We select it. We choose an inlet stream to be NSTRO4. That's all the inlet streams of vapor stream we want to create. The liquid stream we want to create. The energy stream we want to create. The pressure is fine. We're going to override both temperature and pressure. The pressure is going to be 20 bar. Enter. And the separation temperature will be 40 degrees for reasons that we've discussed at length. Cooling water. Okay. Next one. Oh, separation column. That one's not going to change. I'm just going to get it neat. And now we put in our separation column. Right, so let's just talk about these columns before we go any further. ChemSep column, I think is going to be a good column to use, but it is a complete column package, as is distillation column. Absorption column is something that I want to do next week. So in this stream, MSTRO6, we will actually be losing a lot of methanol. And I want to put in an absorption column where we scrub out the methanol using water in the absorption column. And we see how well that works. But today we're going to use the shortcut column because it is the easiest one to get working. And it's got enough options because it does have a partial condenser, which is a really useful, very useful option to have, which you don't get on the standard, what do they call it in Aspen? The shortcut column in Aspen doesn't have that option. It's the, what is that? You've learned about it in mass transfer, a shortcut way of doing columns. Anyway, let's put in this shortcut column. It's going to get attached to the liquid line. Just want to move it. Right, so the feed is going to be MSTRO7. We must create a distillate stream. We must create a bottom stream. We must create a condenser duty, and we must create a reboiler duty. Okay, I'm going to move this thing up a little bit so that we've got approximately a straight line connecting these two. And put the duty up there. This duty over there. This duty we can move down. Okay, so let's look at the column. And the light key component, we want to separate in this column because this is a liquid which will contain water and methanol. Carbon monoxide, carbon dioxide, and hydrogen unreacted are going to be gases in this gas liquid separator. So we were trying to remove as many of the gases as possible. We're removing them at a relatively high pressure. So we're trying to recover as much as we can over there. I don't think high pressure really helps, but I'm using a high pressure here for illustrative purposes to see the importance of using a partial condenser here. So this is water and methanol. Now we go back to the, oops, click that. We go back to what is the light key component. That will be methanol. what is the header key component? That will be water. So those are the two we want to separate, and that's what defines light key and heavy key. It's important, though, that they should be next to each other in terms of the relative volatilities of all the components. And now you can say how much light key, how much methanol can we afford to lose in the bottoms? And we're saying 1%, and how much 1% of its composition will be molar composition will be methanol, and in the distillate 1%, and those are reasonable specs to put into a distillation column. Reflux ratio, I think I chose 1. Let me look on this thing. Reboil at 1 bar. Forgot to put in that. All right, so then I expect you guys would have used you would have used 1.5 as the default. Damn. So let me rather use 1, which I'm pretty sure I used when I did the thing, because we were looking at different numbers further on, and then at least those numbers are going to work out. Sorry, that didn't work out for you. I suppose they would have worked out, but yeah. All right, let's have a look. At least the mass balance would still be the same. Will be approximately the same, because you've got the same specs for the top and the bottom. If you use 1.5, it gives the same condenser temperatures. Excellent. Okay. All right. So yes, it is the same. Whatever reflux ratio you choose. What else did we have to look at? Condenser pressure, and we chose 1 bar for each of those. 1 bar. And there it solves. Isn't that nice? So what I wanted to point out here is what you would have got is, yes, you might have got the same temperature, minus 55 degrees C. You would probably then have got a different number of, I'm looking at MSTR, you would have got a different number of stages. Here I've got minimum stages as 4.5, and you would have got 2 point something or 3. Yeah, Philip, speak.
Prof, I've done exactly the same as you, but my distillation column won't solve. It says there's an invalid value for the distillate rate.
You are using an SCO1, hey, a shortcut column.
Yes, and I also tried both using a total and a partial condenser.
So you've got the same same properties as I've got on the left-hand side here?
Yes,
your
exactly the same.
Exactly the same thing. That's very...
I used a comma and a point both.
You've tried both. Yeah, no, you must always use point. And also in tests, please, because that's what ClickUp understands. So you got Peng Robinson here, huh?
Yes, and I also tried using the NRTL.
Okay, let's have a look at your MSTR07 and just compare your flow rates there, or your components. Do you get the same components as I'm getting? The same amount of the components. Water must be 0.773. And methanol 0.06.
No, I do not have the same there.
Okay, so your problem then is earlier on. So tell me, what do you have for water and what do you have for methanol?
The fractions?
Yes.
So for water, I have 9,7 times 10 to the negative 5. And yeah, okay, that's very small. And for carbon monoxide, I have 0,004. So it's mostly methanol. It's like 99% methanol.
I'm sure that you've ticked methanol in your Gibbs reactor already.
Let me check. No, it's not ticked.
Huh. Okay, check your MSTRO2 and make
Yes.
sure that there's no methanol there. You can see on this one, there's no, under methanol, it's 0.
Yes.
You have got that. Okay, well then, I'm sure it must be this one then, MSTRO4. Oh, why is it not showing? I think I'll just get this down a little bit. There we go. MSTRO4, you should have 0.2 or 0.127 methanol.
Yes, I have 0.28.
Ah, there we go. That's probably where the problem is. So you'll have to just check your reactor, your conversion reactor.
Okay.
Obviously, if it's blue, you must have got the mass balance right, the stoichiometry right.
Yeah, and it's 90% conversion. What did you select the phase in that reactor?
Yes, the phase must be vapor because this is 250 degrees C.
Yes. Okay, I also have vapor.
All right. All right. Well, let's carry on. Right. So this is the interesting thing. On MSTR08, the distillate is at minus 55 degrees C. And now we're going to go and change that to a partial condenser because it's at minus 55 because as a total condenser, we are condensing all of the dissolved carbon monoxide, hydrogen, carbon dioxide it's being dissolved in this MSTR08. And therefore you need to use a really low temperature to keep it dissolved at 1 bar pressure. Remember, we're using 1 bar pressure on the shortcut column. And that's why we have that very low temperature. Now we're going to choose this shortcut column and change it to a partial condenser there. And we're going to have a look at MSTR08, and the temperature is now 62 degrees C. So do most of you get that at least? When you change to partial, you're getting 62 degrees C. Yes, and reflux ratio is still 1.5. That's fine. You did not hit enter after you change. Oh, so it's still 1.5. That's what you mean. Right, okay, thank you. I hate this thing. It's so second nature to me. Get rid of this thing. How do I get rid of this? Oh, wait, let me choose that again. No, I'll choose another one. It's still sitting there. Condenser pressure. Anyway, let's go with it. I can see it at least, so it's 1 enter. And now the pressure temperature is still the same because the mass balance will remain the same. And if we go back to total, we look at that thing, and it's minus 55 again. So it still stays the same. Thank you for pointing that out. Fortunately, it doesn't seem to matter too much. All right, so let's see. We've done condenser temperature, change it. It should be now 2062. Now use a controller block. Okay, so this is cool, but it's not the one I want. I'm looking for something where we can change the temperature from 600 up to 1,000 on the Gibbs reactor, and see how our how the yield changes. So this condenser block is not doing, this logical operator is not doing that, but it is doing something fairly cool. So I just wanted to show you how to use these blocks. We've done a recycle block before, and a specification block. You can also make a specification like the same as we're doing here with the controller block. We specifying that we want 600 kilograms per hour out of this stream. Let's have a look how many there are at the moment. We've got 575 kilograms per hour, 576 kilograms per hour of mass flow in this liquid stream, and that is pretty much pure methanol. And what we want to do is to make that, it's not pretty much pure methanol, it's 90%. But lots of carbon monoxide in there, carbon dioxide in there. Okay. Even at 1 bar pressure, carbon dioxide apparently is soluble in the methanol. So anyway, we want to increase the flow rate of this, which is mainly methanol, and we want to see what conditions of the Gibbs reactor will give us a higher flow rate of this. So the logical op is a controller block. Drag it on. Oops, I don't want to. I want to drag. And the controller block, we want to manipulate the temperature of RGO1. Choose RGO1. The manipulated property is the outlet temperature. At the moment, it's 900 degrees C. What we want to control is that stream flow rate. So it is MSTRO8. The controlled property is the mass flow rate. And there it shows us what the existing mass flow rate is. And we set point, the set point we want is 600 kilograms per hour. That's the controlled property. So you can see here, before I press enter, you can see there the controlled object and the controlled property, mass flow. And the set point we want for that mass flow is 600. So we choose 600 there, enter. And there it goes and puts in all its control things. And the tolerance is very low. I mean, this is 600 kilograms per hour plus or minus like 0.1 grams. So that's fairly ridiculous. Enter. And now we open the adjust control panel and we can let it start the adjustment. Okay, so at the moment, I just want to point out, at the moment, this the current value is still the base value, 575 kilograms per hour. So that's why we have to first open the adjust control panel, and then we can start the adjustment. And it will start solving and change the values. And the manipulated variable is this green, and it is controlling it to, it's making sure the temperature changes until it's controlled at 600. So there's set point is the blue line, and it's been changing the values until the green line is exactly 600. Damn, this silly window keeps popping up where I don't want it to. I can't move it either. Okay. So let's have a look at the manipulated variable. That's the Gibbs reactor in degree C, and it decided it first moved it up. When it moved the temperature higher, up to 910 degrees C, the mass flow rate in the column moved downwards. So it realized, oh, I better go the opposite directions using the secant method to decide how much lower it must go. Chose 570 odd, and then this, because it chose the secant method, this was a pretty good guess towards getting the 600 it required. And then it converged pretty quickly. There's a bit of a glitch over here. I'm not too sure why, because it's going further and further away there. But anyway, it reached the correct. It reached the tolerance correctly after 10 iterations. In fact, after 9 iterations. I'm not sure that there was a 10th iteration here. Ah, damn it. Anybody got some clues how to remove that pop-up? When you right-click, let's right-click again and see if I get something else. I'm left-clicking and right-clicking. Let's right-click in the pressure. No, at the pressure bit. Yeah, because this is all pressure stuff. No. Anybody else? Yeah, maybe it's a bug. All right, well, that's it, folks. Not so difficult. As I say, if you look at this process flow diagram, you can see we've used, let me get back to this control panel, close it. You can see we've used these principles of process creation that you were tested in the test. There we had a reactor. We've got all of the reaction products. We cool it down to 40 degrees C, and that is heuristic number 9 according to the numbering of the heuristics that we've got in our class notes. Heuristic number 10, I think, says if you've got a mixture of vapors, you cool them down using cooling water, and then you can separate the vapor stream separately from the liquid. So yeah, we get a liquid, and it says with a liquid, you use distillation or various other methods, and here we are using distillation. But because there were dissolved non-condensable gases, it was important to use a partial condenser over here. So this is what I'm looking for. There's usually a mark allocated for you showing a partial condenser. This one doesn't show the partial condenser. You should have a line coming up there with the vapor coming off. It looks like you'd have to actually, this would be a mixed stream. And phases, I wish this thing would disappear. Let's move it this way and then we can see what's going on. The phases are mixed. You can see down there at the bottom. The phases of the stream are mixed. So you'd have to put in a gas liquid separator to actually show them. But normally on a process flow diagram, you would show the gas stream coming off that way, and you'd show the liquid stream splitting down here. So this would be typically only a liquid stream. And those vapors you would actually mix with these vapors, and then we put in an absorber. Let's go back to the columns. We put in an absorption column so that we can put in water to strip out the last of the methanol. All right. More questions. I have a question regarding MSTR01. How do you ensure that the values don't change themselves? Okay. I think both in DWSim and in Aspen, as soon as you put in values, then it becomes a non-changeable stream. If you put in values, it becomes non-changeable. I know in Aspen, if you go and delete everything, this one it will be different. Sorry, compound amounts. You can't just delete. So where's your stream conditions? Kilograms per hour. If you, yeah, in Aspen, if you can just delete what compounds there are in the stream, and you delete any mass flow, molar flow. You just delete these fields. It realizes that this has to be a calculated field. So sorry about that. Yeah, so that's it. It shouldn't change. So who was that? Yuri, did you have your MSTR01 changing suddenly?
Yes, as soon as I changed it back to the original values, it changed itself back to 0.333 for 3 compounds.
Oh, maybe you simply didn't push that. You didn't push the accept changes thing.
And that's after I pressed accept changes.
You made sure you did. Okay, sorry. No, I've made that mistake before without pressing accept changes. And no, if it went back to the original thing, I don't know, maybe it didn't accept changes. So when you say accept changes, you have to check that it's recalculated and it's come out blue. I guess that's the only one that you need to keep an eye on this thing at the bottom and make sure. Oh, look at that, it's pressures again just by clicking on this bottom bar. Okay, that's all I can offer for you on that. All right, any other questions? Use dot, not dot. No, use
a decimal comma and not a decimal point.
Oh, I see, right. Yes, it was too small for me to see there's a comma and a point. Oh, you know what? There, you're right. I said earlier you must use a decimal point, but that's because I've set my windows for decimal point. So it will automatically recognize.
Yes, it works. It actually works. Thank you.
Okay. Well done, Michael. No, yeah, regional settings. That's it. Yeah. Okay, good. Right, now we've got, and I suppose those regional settings would also work with ClickUp and the exams and tests.
No, it doesn't
So
work for ClickUp or Python.
Okay, so you have to use a point in ClickUp.
Yes.
Okay. All right. That's extremely important to know. All right. Good. Well, that's another mystery solved. A good thing about these tuts. All right. So I'm glad that DWSim is working nicely, and I'm getting more and more impressed with DWSim now that we've got the Gibbs reactor working. So yeah. I'm looking forward to putting in an absorber and seeing how well we can recover all of our methanol for next week.
How will we, sorry, Prof, at the partial condenser, there's still only one mass stream coming out. So how will can we like add another one there to add the absorber, or how does that work?
Yes, we're going to have to do a gas liquid separator here.
After the partial condenser.
Yeah, we'll have to put one in because DWSim doesn't put it in doesn't put in a stream automatically there. Let's have a look here. I just want to have a look if it's got no, it's only got these streams that we've actually put in. So by choosing partial, I'm still on total. By choosing partial, it doesn't actually give us the option of putting in another stream there.
Okay, but in real life, the partial condenser will have a liquid and a vapor stream coming off.
Yes, correct. I think you would use your condenser as you would design your condenser so that the liquid and vapor are separated. Yeah, like a kettle reboiler, kettle condenser type of unit operation over there. All right. Any other questions? How's that? 10 minutes early. Ha. Okay, guys, let's call it a day.
Sorry, Prof. There's a question in the chat box asking why would we want a partial condenser instead of a total condenser?
Okay, so Dewald, if we have a look at this temperature of this condenser, the temperature at which this condenser must operate is 62 degrees. And this is because we've chosen the partial condenser here. If we chose a total condenser, it means, now we go to this MSTR, you'll see phases are mixed. It's still phases are mixed. But total condenser means that this entire stream is liquid, and that means all of the dissolved gases are still dissolved. The only way you're going to get all of those dissolved gases dissolved is by having a temperature of minus 55 degrees C. So that's the reason that we want to use a partial condenser. There are dissolved gases coming in with MSTR07. I'm going to just move this whole flow sheet a little bit so that I can see MSTR07. And there you can see carbon dioxide is 2% of that total flow rate that's going into that condenser. Shortcut column, into the column. We've got dissolved gases like CO2. And that CO2, this was at 20 bar pressure at equilibrium. So this was its bubble point. And we went in here, and by taking off the CO2, or the non-condensable gases, let's go back. This is minus 55 degrees. And if we make it a partial condenser, we could take off the CO2 as a gas, and then we don't have to, come on, there we go. Then we don't have to cool this condenser down as low as 55 degrees C. And now we can use cooling water, 62 degrees C. Is higher than 40 degrees C. Normally we'd be limited to 40 degrees C at the condenser. Right, and any other questions on this flow sheet? All right, stop the recording.